So coagulation is this clotting. It's when there's truly a plug forming and the vessel that is damaged underneath within that plug is able to heal itself and repair so that there will eventually no longer be a breach in the vessel wall. And we're going to spend a bit of time talking about coagulation because of the whole process. This is the most complex. The vasoconstriction, like I said, is pretty straightforward and mechanical. The platelet plug formation is just giving you a nice temporary seal to allow this more complex process to take place, because this takes time. So the reason why we're looking at an image here of a domino rally is because we refer to the coagulation process as the coagulation cascade. We have a whole series of proteins and enzymes that are all existent within our bloodstream already that need to be activated. And one will activate the next, which will activate the next, and activate the next, and so on, just like a domino rally. All these dominoes line up, and they are upright, and they stay upright until somebody knocks the first one over. And then once the first one's knocked over, then it sets off this cascade until you get to your end point. And that's exactly the same with coagulation. It is a very complex process, and it's complex for a reason. Like I said, we have all these proteins and enzymes in our bloodstream already. We don't want the blood to clot by accident, because then we have problems. When you have blood clotting in places you don't want it to clot, you end up with things like strokes, embolisms, myocardial infarctions, so heart attacks. And the body isn't able to function normally. The blood needs to be thin. But then on the other hand, there need to be times when we can repair if there has been damage to the vessel. So this complex process where there's multiple steps that have to take place before clotting occurs allows us to control the clotting process so that it only happens when we really want it to. Beyond this, this is where it gets really complicated. There are a lot of different coagulation factors. So each one of these dominoes in this cascade, there's loads of them, and they all have numbers. And they're not numbered in the order that they go. Of course they're not, that would be far too easy. They are numbered in the order in which they were discovered. It would be nice and easy if we said it started off with factor 1, which activated 2 and activated 3 and so on, but sadly not. These proteins and enzymes are all synthesized normally within blood. Like I say, they're there all the time, and they are synthesized using vitamin K as one of the main ingredients. So that's why vitamin K is really important that we have that within our diet. People who are vitamin K deficient may well have clotting issues because they're not able to form the factors. And there's also certain medications that we use for patients who are maybe clotting too easily, and we want to prevent that. And what they do is they stop the action of vitamin K. And you'll talk about these things more in human disease in second year. But sufficient at the moment that you know that vitamin K is important for forming coagulation factors. So I want to look a little bit about the cascade, but we are not going to focus on the names or the numbers of the factors. Okay? As long as you understand that there are multiple factors in each process, that's the important thing. There are two ways in which coagulation can be activated, and we talk about these as pathways. So we have the intrinsic pathway and we have the extrinsic pathway. All coagulation will be activated by one of these two. Then they will go through a few steps, and then eventually, regardless of how it's been activated, whether it's intrinsic or extrinsic, they'll come to this common pathway and it all finishes the same. So the intrinsic pathway, this happens when you've got damage to the endothelial lining, but it's not a big breach in the vessel wall. So it's, it's not a major issue. There's a little bit of blood leakage, but you're not getting a lot of bleeding. And it's a slow-ish process, okay? We're talking about a matter of minutes before you get to the end of this pathway. There's a lot of steps involved. There's a lot more dominoes in the intrinsic pathway than the extrinsic, so it takes longer. But we're talking about a less less of a damage, and therefore it's less of an issue if it takes a bit longer. So this is triggered by the fact that the blood in the vessels, in particular the platelets, come in contact with the damaged endothelium. Okay, and we know they're doing this because they're forming a platelet plug. So the very formation of that platelet plug in this damaged endothelial area initiates the pathway. The other end of this is the extrinsic pathway, and this is when you've got a clear breach in the wall. The platelet plug is forming, but you're getting a lot more blood loss. So this is a quicker pathway. There are less dominoes involved here. And the reason why there's less dominoes is because the damaged vessel releases the initial factors itself. Okay, they don't need to be wait to be activated. The damaged vessel is going, I need help, and they're releasing their initial factor. And that initial factor is called thromboplastin. So the vessel wall releases the thromboplastin, which straight away triggers the extrinsic pathway of the coagulation cascade. But regardless of whether that's happened quickly, as in a matter of seconds in the extrinsic pathway, or if it's happened slower in the intrinsic pathway, it's taken a few minutes, we will still get to this common pathway eventually. And these last few steps are important. And this is when we talk about how we go from a platelet plug, which is not very strong and everything's just sticking and hanging on for dear life, to a much more solid structure in the form of an actual clot. Prothrombin activator is the first factor in the common pathway of the coagulation cascade. And I am going to talk now about a few factors, and these are factors that you do need to know. It's the only ones that you need to know the name of. So please do whatever you can to make this stick with you. So prothrombin activates an enzyme called thrombin. And thrombin then goes on to activate another protein called fibrinogen, which then causes fibrin to be formed. So they go in that chain. And fibrin is the key to the clot. It's the key to what holds this all together. So I thought this diagram, or this actually electron microscope image, is a really good example of what's going on here. And this is from the Ross and Wilson textbook, so you'll be able to look at this yourself as well. What fibrin is it's insoluble protein threads, like little fibres. And they take the platelet plug that is already there and they give it structure. It provides us with a three-dimensional mesh, a sort of scaffolding, around which the platelets can properly hang on to. You get white blood cells in there destroying any debris, and you get other blood cells coming in to allow the healing process to begin. Platelets alone are not enough. They've got no energy themselves. Remember when we talked about blood and we said they were actually just little fragments of big cell. They don't have a lot going on. So we need red blood cells to bring energy to the area to allow healing to take place, and we need white blood cells to come in and remove the debris and get rid of anything that may be invading the area. So the fibrin gives it this structure. It's sort of like when they do large building projects and they use concrete and they reinforce the concrete. The concrete itself isn't strong enough, so they build a metal cage first and they put rods down the middle of it, these big metal rods, and then they fill it up with concrete. And it's those metal rods that are holding it all together. But that's what fibrin does. And it's a really, really important part, and it is the final step of the coagulation cascade. So everything that goes on before that, all the loads of factors, that domino rally, they are all coming to this end point where fibrin is created to give structure to the platelet plug that's already formed. But at some point, we actually need to get rid of the clot. So let's move this on a little bit. We've had a vasoconstriction to reduce blood flow. The platelet plug has formed, and that has commenced a coagulation cascade, and now we've got quite a solid thing blocking the breach in the vessel wall. The vessel wall is no longer permeable. the blood is not getting in and nothing from the outside is getting out. The clot initially will start to shrink because it loses moisture. The platelets themselves contract, and it starts to bring the edges of the vessel together so that they can gradually repair and work towards each other. But as they work towards each other, and they're repairing themselves using fibroblasts, and they're laying down new collagen fibres, the clot gets in the way. So we need to start to get rid of the clot as the vessel heals. And this process is called fibrinolysis. So the fibrin is what gave the clot structure, and the lysis refers to getting rid of or breaking it down. So dissolution of the clot. It takes place because of something called plasminogen. And plasminogen is another actual clotting factor, which sounds weird because actually the purpose of it is to get rid of the clot, but it's sort of the last stage in the process, so it is still a coagulation or clotting factor. And actually, as the clot is formed, plasminogen gets trapped in there, but it isn't activated until such a time when the body no longer leads the clot. So when it starts to shrink and the edges start to come together, plasminogen starts to activate. And it quite straightforwardly breaks down the fibrin, starts to dissolve it, and then the white blood cells that are in the area, the big macrophages, can come in and phagocytose this breakdown of the fibrin and take it away. And therefore the clot will start to break up, and you will eventually end up with no clot remaining and the vessel wall having healed itself. So that's really taken us through the process of haemostasis. Like I said at the beginning, we're looking at this at a very simple level, and I don't want you to overcomplicate things too much. If we go back to our learning outcomes, just so I can make it clear to you the type of thing you need to know, you'll notice that nowhere in there am I saying that you need to remember to name factors. The last four in the common pathway is important, and those are ones that you need to be able to recall and draw to mind, but everything else goes a little bit above and beyond what we need. We know what haemostasis is, and we know it's a three-step process. We've talked about that a lot. These two pathways and why we have the two pathways, what each one does, intrinsic and extrinsic, is important, and understanding that the extrinsic pathway is much quicker because it's for when there's been a lot of damage, whereas the intrinsic pathway is a slower, more complex process because it's a small amount of damage that's occurred. Understanding that it is a complex process for a reason, and we don't want our blood to clot if it doesn't need to, so that's why it's a difficult process to get to the end point of. And then how the clot forms itself with the fibrin, and then at the end point fibrinolysis. If you can keep it within this kind of level of complexity, you should be able to understand things quite well. We will obviously talk about this in your tutorial, so if you have any problems before then, please make notes and we can talk about it when we get together.